Okay. So good morning, everyone. Thanks for attending this talk. My name is Lingyi Liu. I'm from machine learning platform team in Netflix. Today, I'm going to present some story of our machine learning use case. Basically, it's a large-scale distributed training of media machine learning models with Amazon FSx. This work is done with our colleagues, Maddie, Clay, and also the Nagendra Kamas. So this is the outline of this talk. First, I will give some very unique media machine learning applications in Netflix. And also one specific use case is the self-supervised video representation learning, which we use this use case to bootstrap these training infrastructures in this talk. And then we will dive deep into the distributed GPU training architectures and also some challenges. How do we evolve these training architectures? And especially how we employ the Amazon FX for Lustre to scale our data loadings. Finally, I will show some result. So as I just said, the media machine learning application in Netflix is pretty unique because we do a lot of video streaming to our users. So overall, the machine learning applications, the goal is trying to optimize or visual representation of our content. So our machine learning algorithm try to develop computer vision models, audio models, and also the natural language processing algorithms and tools to aid the artwork generations, and also to add the video like the trailer generations. And also we do this to enhance the productivities of creation process, and also even post-production such as the quality control and the VFX. All these are very unique applications in the industry. So let's dive into some specific use case. So first example is we use machine learning to retrieve the character-focused videos thumbnail candidates. So this will serve as an assistive tool to narrow down the search space for our creatives. So the task is trying to rank for giving one long format videos. So if you go to the Netflix homepage, you can see each video is always represented as some image or even short-term videos. So the task in this application is trying to rank frames from long-term videos, try to see whether they are suitable for the thumbnail candidate. So the model will we use some convolution neural network, try to measure the face, whether the face has the good face expressions to be a candidate. And also they employ some clustering for different character and try to capture the character prominence and also the relations. So the next application is we also use the machine learning to do the learning the trailer moments. So one pain point in our post-production, the trailer productions, is when we have to pull the creative moments from the long-term videos, and the creatives have to do a lot of watching the long-term video again and again, which is actually very time-intensive. So on the other hand, so you can see the moments in the trailer always manifest some kind of visual patterns, which is very suitable for computer vision algorithm to capture these visual patterns. For example, in the slides, the moments in action trailers, you can see it always show very action, intensive actions. And the moments in romance, it shows also very peaceful. Yeah. So we use some machine learning algorithm which called co-attentions between the trailer and the movies, and also use the contrastive attention to enhance the visual representations. So next one is more we use the self-supervised video representation learning. We use this to bootstrap our training infrastructure, the multiple node GPU training infrastructures. So basically, we want to learn general purpose embeddings of the Netflix video assets. So the general purpose means we want to use this learned embeddings as a features for a lot of downstream tasks. So we don't want every task to train from scratch. So basically, and also this embedding is more like a data content driven because we use the video, we also use the audios, and also even we use some script to get this embedding from the assets. And also this learning is in a self-supervised fashion. So it means like because we don't need any library. Actually, it's not easy to labeling the training data set. And also, because of the general purpose, we don't want to, this learning will be, to pass towards some task. So that's why we use a self-supervised learning. And also, we want to preserve the temporal granularity, which means like the embedding will be based on some intervals of the video instead of the holistic, for each video we generate one embedding. So we can, like, for each intervals in a very long form video, we can generate embedding for each segments. So if you see this slice, so we have the video and also have the audios. So each one fit into different neural network, and then we can combine these embeddings to make a contrastive loss. So basically, like if the embedding are from the same video and the audios in the same intervals, and then it will be a positive pair in the contrastive loss, or else it will be a negative loss. So if you want to know more about the algorithm side, you can dive into the papers I mentioned in the slides. Okay, and then the data set, as I just said, so we have this ID of the samples, so which points to some specific intervals of some specific videos. So we give the sample I, for example, the index. We actually index to some videos, and then we extract the corresponding clips from that video, and also apply a set of pre-processing functionality. So, and then we get the video frames, and also we get the audio like spectrograms. So the video frame will go to a very classic resonant network. It can be configurable to 18 layers, 15 layers, or 101 layers. So the convolution layer is 2 plus 1D. It means like the spatial convolution plus the temporal convolutions. And the audio spectrogram will send to a classic resonant 2D network. And then we rely on the projection head to map this embeddings to common dimensions. And then we can we can compute the contrastive loss. So this is the model architectures. It's a pretty like adoption, like very classic model architecture. And then we start with this. You can say the V0s. We basically download our video asset catalog into the local like SSD disk because it's a bit faster. And then we start a lot of like this loader process. Because like we use the P4 instance, so basically they have the 96 CPU, which can be used to load this data in parallel. And then for each process, they load one video, and then try to extract the clips in that videos. And then they apply the preprocess. And then they form some batch, and then send to the GPU training process. So the GPU training process is copy that to the GPU memory, and then apply the standard training pipeline. For example, the forward, backward, and loss computation, and then backward to get the gradient update. And then even we can scale this, to multiple GPUs and also to multiple nodes using the data parallelism. And also this employs the connected communications among the different GPUs to get all reduced gradients update. So this is V0. So that we face a lot of challenges in this V0 versions. I think first we have a much bigger data set because our movies and TVs in our catalog is much larger, and also this keeps increasing. And but like the P4 instance, which I believe is the largest one in provided by AWS, the NVMe is only like 8,000 gigabytes. And also we have larger like rotational drive, but it's slow because this access is random access. So if you use a rotation, it will be very, very slow. And also we want to do the multiple node distributed training because we have so much data set. So it means like when you use a distributed training, you have to duplicate the data set across the nodes because every GPU will randomly access the video and the clip. And also after each epoch, we have to shuffle the data set. So it means like every node have to maintain an entire copy of the data set. So this is actually not very efficient in storage. So another more fatal challenge, I would say, is like the low GPU utilizations. So it means like GPU are mostly waiting for the data loadings. Yeah, this is really bad for given the GPU is pretty expensive resource. So it means like the more we use GPU, the more we waste. So we won't really want to solve these low GPU utilization problems. So basically, we can say like we did some profilings about the data loader process and the training process. Basically, the data loader process is trying to do is like giving an index. I found the corresponding videos, right? I load the videos and then decode the videos. And then also we extract the clips in that videos. That's what you need, right? And then we apply the pre-processing on this very tiny fractions of the large videos. So if you can check the profiling result, you can say like in the left side is the data loader process. It most spend a lot of time on loading the videos and decoding the videos. And then also a lot of time to do the pre-processing. And on the right side is the trainer process. So you can see like the GPU is mostly idles. They are waiting for some kernels to be scheduled. So, and then they finish very fast and then wait for the next batch to come in. So most time the GPU are wasted in this scenario. So let's step back to see the industry, the state of the art in the industry, right? So we have hardware and software to support this. In terms of like computation, right? We have very high-end GPUs from NVIDIA. We have V100 and then we have A100. Gives like hundreds of teraflops, computations capabilities. So, and also, we have a lot of like software. We have like, for example, the TensorFlow from Google, they provide a high-performance operator library, and the PyTorch also have the same functionality support. I cannot say it's perfect, but the situation is much better because so many people are working on to optimize these computations. And also, even there's some like compiler, new operator libraries generations, which is much more efficient. And also, the GPU communications is also in a pretty good shape. We have the hardware like NVLink backed, the GPU RDMA. And also, AWS also have the Elastic Fabric adapter to support the cross-node communications, which is super efficient. And in the software side, we have fast or reduce and other connective communications by the NICA libraries. And I would say the biggest issue is how do you get the fast I/O to ingest the data in the GPU memory? That's the most challenging part. Yeah, but not many people are trying to solve these problems. Yeah, and also this problem is difficult. Is very ad hoc because it depends on your applications. Yeah, and in our case, right, typically like we need like 5 to 8 gigabytes per second ingest throughput per node with 8 GPUs for A100. And also we have like 100 terabytes data. And also, as I say, like after each epoch, we need to shuffle the data, right? We hope like it's more like a global storage. And then we can automatically get the shuffling functionality instead of copy the data around. So this is the state of the art in the industry. So, and then according to the profiling result, we try to revisit some data loading pipelines toward the saturated GPUs, because that's the most challenging part. So as I just said, we have spent a lot of time to do the decoding of a very long format videos. So in that case, we can actually pre-compute all the video and audio clips to save this video loading and decoding times. So, which actually is a very minor change to data loader. So basically before your training, right, you do these pre-computations, and then basically to load all the samples. And then during the loading process, you can write this out to some storage, and set some like map from the index, the sample index to the real like clips, and then you can reuse these pre-computed clips in different training again and again with different hyperparameters, because this were unchanged in different training paths. And also we try to retain some unchanged computation in the pre-compute. This, for example, you read the videos, decode the videos, extract clips, and also even have some resample. So this is always like unchanged part. So we just freeze them in some storage to save some training time in the during the training. So and also, like I just said, there's also some changed part. A very simple example is like people want to do some data augmentation. So you ingest some randomization of the data. So we want the data to be changed in every training epoch. So in this way, we have to offload this change part to the GPU computations instead of keeping on the CPU. And also, we can do the batch transformations, because like originally every CPU just makes some transformations on the single samples. And then because the GPU will get the whole batch, so they can apply the batch transformation, which is much more efficient than originally transformation done on the CPU side. And also, we put it at the beginning of the training pipeline. So this will involve some reordering of your pre-processing steps. Just separate the unchanged part and the changed part. So and then like in the GPU side, you just copy the data to the GPU memories, and then apply this batch pre-processings on the GPU, and then send to the training pipelines. So I think one natural question coming out is like how to efficiently like store and access the audio and video clips. Because originally like the video, right, you have maybe like a simple example, you have 1,000 videos. Now you already have to cut it into maybe millions of like clips, which actually exploding of the size and also the number of files. So how do you handle this? And I think we explored different solutions. It seems the Amazon FSx for lectures gives a very the best solutions for us. So basically, is a high performance network file system, which actually is very popular in the HPC community, and also it provides massively scalable performance. So if you see on the slides, this is more like our training architectures. We have a GPU training cluster, so which has like multiple nodes, and each node has 8 GPUs, and all of them can talk as the FX client to the Amazon FSx to get the data. And we store all these pre-computed clips in the FX for last year's instance. And also, it can support the scalable loading of the data for multiple node GPU machines. Let's just say, like we have multiple clients to access in parallel. And also, the FX gives very scalable performance for the reading. And also, one good advantage is we could automatically get the support of data shuffling, right? Because it's a global storage. So we don't need to move the data around. Just one copy should be enough. And also this, like I just said, we have so many clips, and also each clip becomes larger because we store the original tensors. So that's one, we did some optimization of this part to trade off the computation and storage. So as you know, like we have, for each one P4 instance, we have 8 GPU and 96 CPUs. So if you just load the data, use the CPU to load data, actually most of the CPU will be wasted. So we did some optimization. We try to encode these tiny clips in the clips into the storage instead of storing the original decoded clips. So this will massively save the space. Because Amazon FSx is also pretty costly, so that's why we can save a lot of space in this aspect. So, and also we take our advantage of these 96 CPUs to decode the clips during the training time. So this is more like a trade-off between the computation and the storage. And okay, let's recap the whole evolved like the training architectures. So first we have some CPU like task. We don't need a GPU for the pre-compute. So basically we apply a pre-compute process to load all the videos, apply the pre-computations. We get the extract video clips. Basically, for each clip, we store some maybe 16 frames of the clip and also the audios, sometimes the audios, and then store all this in the FX instance. And then in the data loaders, and then this will be pretty lightweight. Each CPU will load the clip, very short time of the videos, and then try to decode it, and then it's done. And then they are sent to the training process. The training process copy the data and then to apply the Bayes transform, and also some pre-processing functionality on the GPU, and then sent to the training pipelines. And also it can also be applied to multiple node, multiple GPU, multiple nodes. So that being said, we also did a lot of tunings to get the best performance from the FX for Lustre, according to our specific use case. Because the Lustre FX is not specific for machine learning. So for example, we have a very unique read-write patterns. Each clip is only read once, basically, in each epoch. And also it cannot be reused across epochs, because it's really long time. And also, we write clip file is also once in the pre-compute. So, but I think the FX did a lot of optimization to cache a lot of files in your CPU memories in the client side. So actually, we tuned the max cache MB parameters to reduce the client side memory usage. This is very important because else because we have so many files to write in the FSX, and then they cache a lot of files in the client side, which will slow down the writing speed a lot. So we reduce basically we get rid of the cache. You can think it. And also we try to tune the RPC cores in the flights to increase the concurrent RPC numbers. And also we try to analyze some read-write statistics, such as the offset RPC stream and IO side to change the placement of your files, the clips files in the FSX to get the best performance. And also, I think the latest FSX developed some data compressions to save the storage. So we may try this in the next steps. We can save some storage cost, and during the reading, the FX server side will try to decode the data. So I think finally we apply this FXs and did a lot of experiments. I think the first one, the result is really amazing. So we define this throughput as a measurement of the training speed. So basically, it's the number of samples ingested by the training system per second. So first one is we compare with the V0. So V0 is no pre-compute, no FSX. And then in the V1, we apply the pre-compute. We did this on 2 GPU, 4 GPU, and 8 GPUs, and even multiple nodes. We can consistently get 3 to 4x throughput improvement with this pre-compute and Amazon FSX. So this is really amazing because it can reduce the training time maybe from week to maybe 1 or 2 days. So this is really speed up the algorithm iterations and create more innovations. And also we especially did some experiment about a different kind of workload. For example, the first case is the model is very small. So you use 18 layers ResNet. And then it's bottlenecked by the data IO side. So basically, ideally, normally we will try to overlap the data IO with GPU computations. So because the GPU is a small model, the GPU computation is very fast. And then the whole time is spent on the IO side. So we compare this with the local SSD. So definitely, it will be slower than the local SSD because that SSD is super fast. But I think that one good thing is we can see that the FXs can scale linearly for workload with the IO bottlenecks. For example, from 2 to 4 GPU to 8 GPU, because we are keeping adding more and more reading process. We can see the throughput keeps increasing linearly. Another thing is comparing with the SSD, we can see the Amazon FSX is the most scalable to parallel readings. So when we have 4 GPUs, which means less number of reading process, we can get about 60% of the SSD throughput, local SSD throughput. When we use the 8 GPUs, so which maybe doubles the number of reading process, we can say it now increased 71% of the local SSD performance. This is really nice. And another case we did is the deep models. So we can say like 100 layers of the resident network. So we can say like now is completely like bottlenecked by the computations. So that's what we expect because we want the GPU to dominate the cost. We can see like we constantly get the same performance as the local SSD. Yeah, because it means like for our like media workload, right, with the model computation, the I/O is no longer the bottleneck. Everything is on the GPU side. The GPU side is 100% like utilized. So what we can do is like to optimize the GPU kernels to get best from the GPU side to get it faster. And then the last one is the distributed training workload. So we scale in the multiple node distributed training with the FS instance. So we can see like, of course, first the I/O is no longer the bottleneck from the 2 GPU to 8 GPU to 24 GPU, even to 32 GPUs. So we can see the throughput keeps increasing linear. It's not linearly, but because we have the communication among the GPU node. So, but we compare with the PyTorch, like the DDP, that distributed trainings. So the scalability is roughly aligned with them. So this is, it means like the I/O is no longer the issues for us. And also from the FX server side, we can see like when we increase from 1 node training to 3 node trainings, so which is 24 GPUs, we can see the output, the throughput is also like triples. So which means like the server side is very, very scalable for you to read from multiple clients. Okay, and there's several takeaways. First one is I think pre-compute all the training samples could resolve the decoding and the pre-processing bottleneck in the training of the media machine learning models. And FXX for large network provides a very scalable solutions to store these pre-computed samples. And also the FX philosophy is also scalable for multiple node distributed training support. Okay, I think that's my talk. Thanks so much.